thanks for coming here today. I'm trying to give you a very compact overview of a few works we've been doing the latest years on this nice topic in tight cooperation with Ericsson. This is very much related to standardization activity also in the ITF. So what's group communication in the first place? At a high level, it's quite intuitive, but in principle, it's about achieving efficient delivery of messages in a group of, in this case, especially IoT devices, grouped together in a common set according to whatever criteria. Practically, you have the possibility to have a sender device preparing a message, typically a request, to be sent at once as a single message to all other members of the group, technically over IP multicast. And that requested device is going to get multiple responses bound to the same request from, let's say, all the other members of the group. Of course, responses go instead as unicast message back to the original requester. Bottom line, you have a performance benefit because you send around less messages, especially from the client side, so you have more bandwidth left available for other devices or application, and you reduce latency processing, especially from the client side, of course. This model for communicating started for other kinds of more generic networking application, and recently it has been approached more and more also for IoT use cases, about which I have a few slides in a while. But first, while security and legal at least special here rather than in point-to-point or pairwise communication, well, you have also to bound from a security point of view multiple responses to a single request. You have to preserve source, and I stress source, authentication of sent messages in the group. More on that later. You are going to lose that the moment you move to a group communication model and you have to reintroduce it, guess what, through digital signatures. You have also to take particular care of management of key material in the group, provisioning to new group members, revocation and renewal, and so on. More on that later on too. In the rest of the talk, I'll refer to the word group, thanks Ludwig, as a security group. Meaning including members that share common group key material that they possibly use to derive further key material. And a security group in that sense can be mapped with other kind of views for group, like network groups, so devices commonly using the same multicast IP address, or application groups, so devices essentially running the same application for the sake of payload handling and processing at least. If your typical catchy use cases in the latest years at least that are trying to come up and use the group communication model, it seems like the most interesting and successful one is about lighting control. So bottom line, grouping a number of smart lighting devices, for instance, into a given room or another room, and guess what, you map each group to each room. And you have, in the very simplest case, a switch controller device triggering on and off, or dimming, or switching back and forth all light bulbs in the same room and group at once. And of course, responses are supposed to give a feedback and status support for such devices. You can naturally extend this use case into the second one, integrated building control. You can essentially consider a wider set of devices with a wider set of commands you can send to them. Well, a totally different use case instead is about a more efficient distribution of software and firmware upgrades to a bunch of devices at once, of course, reducing the network load and the propagation delay for firmware images that are supposed to be pretty large in size. And you can have, well, a variant of this when it is about not really distributing software, but updated values for parameter and configurations on such device. Right. What you need to have this in place in a secure way, of course. If you take a device just deployed from a chronological point of view, you have to go through these 3 steps. So you need to find out the groups in the first place and the information you need to join them. You need to provide to new group members key material to take part in the secure communication in the group. And then finally, you need to communicate, which is what you care the most, of course. So actually, let's start from the end and move backwards. And that's, in fact, the way the order we took this work in the latest years. Some background first. The starting point is really that the CoOp protocol that I suppose most of you here know is just a de facto application layer protocol in the IoT. They would deserve a separate talk, but think about it as a very light version of HTTP, just running typically over UDP. Fair enough. Then what? Well, CoOp natively supports two nice things. Communication for groups over IP multicast, and native support again for proxies used as intermediaries in a number of use cases. So this is just great for our particular problem. About security, CoOp doesn't specify itself any particular solution, but it clearly points at DTLS. And the DTLS protocol provides security all or nothing as a secure channel at the transport layer. And this is not exactly the best thing in our case for two reasons. First and foremost, DTLS doesn't work over multicast. Simply, it doesn't. It's not designed for that. It just assumes two communicating parties that establish a channel between one another. So you can somehow still build up a kind of secure group communication using DTLS, in the sense that if you have 3 members in the group, the sender can create 2 equal copies of the same message, establish 2 separate secure channels with the 2 recipients, and send the same message over the 2 different channels. And of course, it can get back a response over the respective channels. So essentially, you can still deliver messages in a secure way, but all the performance benefit of the group communication model are lost. The second problem is a little bit more complex, and you actually have it in the first place in the unicast communication model, and you just inherit it again the moment you make it even more complex in a group communication context. You typically deploy proxy units as intermediaries, typically to enable asynchronous communication with servers that can be dormant for a while because of power saving reasons, and proxies can help a lot for caching. If you use DTLS, you have to face and accept 2 things. Again, you communicate over secure point-to-point channels, so from client to proxy, and then again from proxy to server on 2 different channels. So essentially, the original message sent from the client is decrypted at the proxy, and at that point the proxy can do whatever it wants undetectably, can see whatever it wants, possibly change something, and then it has to re-secure that and send it to the server. So the 2 cons are that you have a double security processing at the proxy, and you actually need to entirely trust the proxy. That can be an acceptable trust model in your use case. As an alternative to that, you'd like something, of course, similar to end-to-end security, where the client produces the actual message intended for the final recipient, and it's secured in a way that only the server can have full access to that, but still you need to still enable the proxy to be able to perform the intended intermediary operation. And about that, this is coming up from working cooperation with Ericsson and RISE, which is an advanced standard proposal providing, in fact, end-to-end security and fulfilling those requirements at the application layer, essentially within CoOp, using the standard CBOR, eCOSI for the sake of efficient encoding of information, also security related, so also ciphertext and even keys if needed. It essentially works wherever CoOp works at the lower layers, support for all the possible functionalities and options now related to CoOp. Usable also when HTTP is mapped to CoOp, and OSCORE has been recently introduced in the latest version of the lightweight machine-to-machine standard as the application layer security approach as an alternative to DTLS. It can coexist with DTLS if you really want to use both at the same time. How it works in a nutshell, because details are complex, CoOp messages can signal that they are OSCORE protected with a new OSCORE option introduced through this work. The 2 communicating parties here, I'm starting from 2 endpoints that will extend it to the group case. They share a common set of key material and parameters grouped into a structure called security context. And really in a nutshell, OSCORE takes a CoOp message to protect, it secures it, it wraps it into a COSI object, and it delivers the result as a secured CoOp message, essentially delivering the secure part. And the nice thing is that you can selectively protect different parts of the original messages. So some parts can be encrypted and authenticated, for sure the payload, or some options you care particularly about. Some CoOp options can be integrity protected only, so they are visible to the proxy. Some parts can even be neither encrypted nor protected. Okay, just a hint of what I meant with security context. Those are 2 peers. That's their data structure they share. The security context is composed of a super common part among the two peers, and then they essentially partially mirror the two respective other parts of the security context. So each device has in the context a sender part and the recipient part. And given a device, it uses the sender part to secure outgoing messages. Doesn't matter if they are requests or responses. It uses the recipient part to unsecure incoming messages, regardless they are requests or responses. So time-wise, a client prepares a request, it secures it with the sender context, sends it to the server that uses the recipient context to unsecure the request. The server prepares a response, let's say it secures it with its own sender context and sends it back to the client and unsecures it with the recipient part. Essentially, and here it starts with the actual new work, we are extending our score to make it work also in secure group communication context. I have to admit we started for very, very good ground with the native score. Still, there was quite a lot of work to do to extend it, although it came up natural. We need, of course, to fulfill the very same security requirements you feel with OSCORE. And well, I can anticipate that that's just true already. You are able to bind security groups you create with group OSCORE with whatever other application or network groups. You have 100% flexibility with such a mapping. Some aspects that are not directly addressed by group OSCORE are the provisioning of key material to new group members and the group discovery that is treated separately. I have a few slides also about that. How is this extended? We have to introduce a few concepts. You have a group manager, which is an additional entity that is typically assumed to be not constrained, but well, if it can, you're welcome anyway. The group manager can be responsible for multiple OSCORE groups, coordinates the security aspect of it, and especially the joining of new members, ensures uniqueness of group and group members identifier. And it's also used as repository of public keys for group members, and that's about the signatures side for source authentication. Here, of course, the main thing related to the group communication model in the first place is that CoOp clients can also send CoOp requests over IP multicast, and servers can, if they want, reply to multicast CoOp requests. Of course, responses are sent separately over IP unicast, and they are bound to the respective request. We also introduced the particular concept of silent server, so it's essentially a server that never replies by construction because its application doesn't need that to possible requests received within the group, and that has a number of advantages, essentially in the number of keys you have to distribute to that node and that it has to store. This is from a very high level point of view what happens. So on the left you have a first stage of communication where a client sends a secure CoOp request, secure with group OSCORE, protected with, you can guess from the same lock used on all the errors, just that key, to put it simple, one key. They are all able, the servers, to decrypt such requests, and then the two non-silent servers reply with separate unicast responses that they protect differently, so using different keys, so to say. But that's still the client, when getting them, is able to unsecure and process. A little bit more in detail on some technical aspect. Of course, we are reusing essentially all the structure mechanisms of OSCORE, extending the signaling OSCORE option accordingly for a few more details. And as I said already, responses are just bound also from a security point of view. The multiple responses to the same request are bound to that request. As I mentioned before, the moment you move to secure group communication, you just don't have source authentication for free anymore. If you think about two endpoints only, that's like an extreme case of a group of two members. Well, you receive a secure message, either it's the other guy or you are talking to yourself, so it's just easy. The moment you have multiple members in the group, everyone in the group has in principle the material to pretend to be some other member. So you need to be sure now the message is coming exactly from that sender. Essentially, you achieve that through digital signatures, and we're especially referring to one of the cutting-edge standard about that. This is actually pushing manufacturers to start considering seriously implementing that signature scheme in hardware, because it might take too long to produce those signatures in software, which I think is good. signatures are just produced and appended right after the payload of the secure CoOp message. About key material, of course, something is shared really by all group members, and they use that really shared chunk to derive individual key material that they also store locally. The individual key material is the one used actually to protect secure messages that circulate in the group. The security context is also extended, so some more information in the super common part, in particular identifier of the group and the exact counter-signature algorithm you use to sign. The sender context now contains also the private key of that device that it uses to produce the signatures. In the original version of OSCORE, you used, of course, to have only one recipient context to process the incoming messages from the only other device. Here you have multiple other device, your group peers. So in principle, you might need one recipient context per other member. So each of the recipient contexts on a given device is associated to another group member. And it includes, other than things you already have in OSCORE, also the public key of that other group member. The nice thing is that a group member doesn't need to have all those recipient contexts at once from the beginning. They are generated runtime the moment this device gets a message from that other peer for the first time. It's easier than it may sound, and I have an example to clarify. A very simple example with a group of 4 members. For simplicity, one is configured as client only on the left. The other 3 are configured as server only on the right. So no previous communication, no establishment, nothing. You start from this, every device with a common context and its own sender context. Pay attention to the match between the sender ID and their own endpoint ID. So first step, the client prepares a request, sends it to the group, securing it with its own sender context. The request arrives to all the servers, and at that point in time, each server is able to generate the recipient context associated to that client and unsecures the request. Each server prepares a response and secures it with its own sender context. The response is addressed separately to the client. The client receives all 3 responses, and at that point in time, the client is able to generate 3 recipient contexts, one for each of the servers sending the response, and unsecure the response. So if you repeat this again with another round, you don't need to generate anything anymore, just the process message. Unless you add, of course, new group members, then some more recipient context is going to be generated the moment those members become active and communicate. This was about the actual secure message exchange in the group. So now we take a step backwards in that list of 3 bullet points, and we consider the provisioning of key material, especially to new nodes that join a group. And as I mentioned, that's handled mainly by the group manager. Of course, only authorized devices are the ones you want to be able to join the group. Again, interacting to the group manager that has essentially to validate the fact that they are authorized to join. If a device is authorized to join, upon joining, the group manager is supposed to provide that device with the key material necessary to be part of the group. So essentially, the common security context and the number of other parameters. Credits to my colleague Luke Besides for this picture. I keep on reusing several times and for the main work on this. To not reinvent everything from scratch, we try to address this problem, and that's what we are doing, building on the ACE framework for authentication and authorization in constrained environments. There is also another advanced standard proposal in the ITF in cooperation with Ericsson and other partners. This framework builds on the well-known OAuth authorization framework, and it leaves to separate specifications called profiles, details about the security and communication protocols you used among participants. To give you the intuition, because that would deserve a totally separate presentation, you have a client that wants to access to a resource server exporting resources, and you want to do that in an authorized way. So the client first contacts an authorization server that enforces access policies on behalf of that resource server. And the client gets an access token to show later on to the resource server, plus additional information. The client can provide the resource server with that access token, show it has been authorized to access it, and those resources in particular. And it can back a representation of those resources, plain values in this use case from the resource server. So if you got this model, then you can guess that it's fairly easy to map what we need and the joining interaction we need on top of the ACE framework. Essentially, a new device that you want to join the group is the ACE client, and the group manager of the group is the ACE resource server. So the joining device contacts the authorization server to get an access token that shows to the group manager saying, I'm authorized to join this group exactly at you. And then new details come when the group manager in interactions 3 and 4 essentially is supposed to provide the joining device with the keying material to take part of the secure communication in the group. More practically, as a resource server, the group manager hosts one join resource per group it manages. So the joining node as a client practically tries to access a join resource at the group manager. And as per the secure communication used to secure the segments between the participants, that's just transparently left to the security profiles of ACE. In this context, the group manager takes care also of another problem that also deserves a separate talk, because it is quite complicated. It's about revoking and renewing key material in the group for the sake of the devices already present in the group. That's commonly known as a rekeying operation. In the approach we have been working on, we are already providing a very simple yet complete approach to do that, but of course there is room to include on top of that more sophisticated and more performance efficient approaches in particular. In a nutshell, you might have applications that really need to preserve backward and forward security in the group. So you are supposed to renew the key material in the group upon a new member joining the group to be sure it cannot have access to communications happen before it's joining, even if it recorded it, or after a member leaving the group to ensure forward security, so that after its departure, that node is not able to participate actively in the, possibly actively in the group communication any longer. Last step, which was the first bullet point, moving further backwards, this is yet another piece of work we have just started related to this. Talking with some people from the industries, we noted that you actually have a problem at the very beginning. You deploy a device in the field, and that device might not know anything at all, or probably, well, not the full set of information it needs to find the group and join it. So how do you address that? Are you supposed to install something no matter what at manufacturing time? That might not be possible either, or what you require to install is too large in size to be done at manufacturing time. Or information you might even be able to install so early has changed over time when you actually manage to deploy the device. As extreme corner cases, you might have deployed your device before the group manager or before the group manager creates the group. We have started to work on an approach to solve this that essentially builds on another advanced standard proposal at the IETF called resource directory. Just to give the intuition, a server device has the possibility to register itself and the resources it exports with the resource directory. And then the client device is able to query the resource directory, and there are very well-known techniques to find out the resource directory in the first place. And so doing, the client device can retrieve updated information on that server, its resources, any point in time. So guess how we are using all this? The group manager registers itself at the resource directory and the join resources it is exporting. And so doing, you can deploy your IoT device anytime, and interacting with the resource directory can retrieve all the missing information to join the group. By doing so, we are also handling the corner cases I mentioned before, because by using the observe option of CoOp, it is possible for that device to get automatic notifications from the resource directory in case of need. So even if the group manager is deployed very later on, eventually the device will know through observe. Just as a reprise, now that we have more information, so what do you need to achieve secure group communication in the IoT? You need to discover groups in the first place. That can be done through the core resource directory. You need to provide key material, especially to new members or intended new members. You need to perform actual secure message exchange in the group. You do that through group of score, which is essentially on its way, hopefully, to become the way to secure group communication for CoOp. Just a quick note on dissemination. Again, this is a tight cooperation with especially Ericsson and University of Duisburg-Essen, with a lot of activity under the Internet Engineering Task Force. There's been strong interest from strong players and stakeholders thinking about especially Federal Alliance and OCF. I really recommend you to read the white paper Federal Alliance released March this year about the security architecture they consider for IoT smart buildings, where these works are mentioned as the way to secure group communication. Big thank to two funding agencies that are supporting us on this, EIT Digital and Vinnova. Side information, Vinnova is also supporting an IoT security event at RISE on December the 12th. You can find more information with the flyers we left at the registration desk. This concludes my talk. Thank you very much indeed.
Thank you, Marco.